Horizon Homes and this is the insane engineering of the SR-71 Blackbird. Well, channel, real engineering. Yes, this is the channel I've been reacting to recently. Yeah, I've been into this rabbit hole of military equipment. It's when you say military equipment, it makes it more specific. Let's just say technology at its peak, right? Because one thing I realized that when it comes to military, anything defense, that's where the technology peaks, and from there on, it trickles down to everything else, civilization. So basically, we are witnessing like peak of any technology. So this is like Blackbird, basically one of the most famous plane ever. The people who don't know anything about anything, doesn't matter which part of the planet, doesn't realize what jet is what, they would have heard of the name Blackbird somehow somewhere. So yeah, I saw the mustard video on it and realized that this plane was so insane that it basically, some of the plane disintegrated around the pilot, which is like insane. It's 3+ Mach speed, right? Now I know there is a plane X-15, X-15, right? The NASA plane or whatever, the manned plane, but the fastest one that ever is like the 6,000 miles per hour or something, which is like obviously faster than this. How is that working? If this was disintegrating at this speed, that was Mach. I don't know what Mach is that. I'm guessing it must have been like technically a plane X-15, but it's mostly a rocket or something. That must have been the case. So this is like a proper jet, which is like one of the fastest one ever, which was so costly and so insane they nearly obviously stopped making it because it had issues, or like I said, disintegrating everything. And then like satellite drones came about, so why you need it? But this was literally peak of it. So it's gonna be fun seeing how real engineering explains this, because I still don't know that much detail. I'm pretty sure most of the video was very short. So yeah, this is gonna be fun. That's for sure.
It's hard to explain the engineering marvel that is the SR-71 Blackbird, a long-range plane capable of flying 26 kilometers above the surface of the planet, so high that the pilots could see the curvature of the planet and the inky black of space from their cockpits. It flew so fast that the engineers had to develop entirely new materials and designs to mitigate and dissipate the heat generated from aerodynamic friction. Entirely unique engines were needed to function from 0 all the way up to Mach 3.2, dealing with the myriad of problems like cooling, fuel efficiency, and supersonic shockwaves interfering with airflow. A plane so advanced that when it detected a surface-to-air missile, its response was simply to change course and speed up. Even though the missiles had a higher top speed, they couldn't achieve the range and high-altitude maneuverability the Blackbird could. This allowed the SR-7.
Yeah, you are going faster than sound, and that wave is interfering with how air basically is supposed to go inside the engine or whatever, basically aerodynamics of it. That sentence alone is so ridiculous. Imagine saying that to somebody like a few centuries ago. This is some next level shit. Put it into perspective, you're making something go faster than speed of sound that is causing these waves, basically, that is interfering with airflow. That is an insane statement.
71 to run hundreds of missions through Vietnam, North Korea, and Iraq without ever losing an aircraft to enemy fire, despite multiple attempts. The entire plane was built around the propulsion system, which alone
Mark 3.2. What is that? Oh, that's a play. Oh, it's gone.
Was a miracle of engineering design. For one, no turbine-driven jet engine can operate with supersonic flow at its inlet. Yet, this plane was powered by the Pratt & Whitney J58 turbojet engine. But get this, off the shelf, these engines could only provide 17.6% of the thrust required for Mach 3.2 flight, a speed which the SR-71 could cruise at for extended periods of time. How on earth did it manage that?
Yeah, how
In
that
order to achieve those kinds of speeds, a ramjet is typically needed. A ramjet, as you can probably guess from the name, relies on ram pressure to operate. Ram pressure is simply the pressure that occurs as a plane rams itself through the air. So, as the engine moves through the sky, it funnels this high-pressure air inside. Before entering the combustion chamber, the supersonic airflow must be first slowed down. This basically acts like the compressor stage of a normal jet engine, elevating the air pressure before it enters the combustion chamber. Once the air enters the combustion chamber, it is mixed with fuel and ignited. It expands and accelerates once again out of the exit nozzle. With no moving parts, this type of engine is capable of flying at speeds far greater than a typical turbine-driven engine. But it cannot start from zero. It needs forward movement in order to achieve the correct compression of air in the combustion chamber. So, they are either dropped from a conventional plane, have a secondary propulsion system, or are a hybrid of a conventional jet engine and a ramjet, which is precisely what the SR-71 used. The turbojet J58.
No, I don't know, but I'm pretty sure like there are turbos that people use in cars basically. They call it afterburner, which I don't know. I could be wrong, but it uses similar thing. They also like, isn't there like a Dodge Challenger Hellcat uses ramjet technology as well, just to funnel that kind of power? I don't know. That might be different, but yeah. Obviously, this is like this is how ramjets work. I'm pretty sure. Wait a minute, this is Blackbird is really old. Did this start with Blackbird? Because I know this technology. A lot of jet uses this, but I don't know when it started. So is this like a first thing for Blackbird?
Engine of the SR-71 is nestled inside the nacelle here. In front and around the J58 is a complicated system of airflow management. These control mechanisms allow the propulsion system to transition from a primarily turbojet engine to a ramjet engine in mid-flight. First, the inlet spike. It is capable of moving forward and back by 0.66 meters. This adjusts the inlet and throat area, which controls the airflow entering the engine. It also keeps the position of the normal shockwave at its ideal position between the inlet throat and the compressor. This is the most efficient position for the shockwave, as it minimizes the energy lost due to drag as air flows over the shockwave. The inlet spike stays in the forward position until Mach 1.6. After this point, it begins to move backwards by 41 millimeters for every 0.1 increase in Mach number, keeping the shockwave in its ideal position. The inlet spike contains perforations which connect to the outside of the nacelle through ducts. Initially, the airflow will come from the outside in to provide additional airflow to the turbojet engines, but once the plane hits about Mach 0.5, this airflow reverses. As the plane speeds up, the inlet spike develops a significant boundary layer of air. A boundary layer is a layer of very slow-moving air that clings to the surface of objects. By bleeding this layer of slow-moving air off the inlet spike, it frees up a greater area of the inlet area for high-energy, fast-moving air, and thus improves efficiency. Around the engine,
holy shit, aerodynamics at its best. This is so good. Yeah, I saw that layer thing in F-35 video from this, like how that was an issue, and that could cause problems with the fan obviously. But in this, like, they literally have a vent that prevents that at a higher speed. Man, seriously, this was an insane engineering. When was this first used? Like 1980s or something? For something like this happening back then, Soviet probably had no answer to this around that time. Not even close to it. This is if you show this to anyone, they would think like, wait a minute, when is this from? 2005, 2006, 2010s maybe? But nobody would think it that back.
There is a bypass area which takes air from the inlet and bypasses it around the J58 engine. This air was used to cool the J58, which again improved engine efficiency and allowed the plane to fly faster. After the air passes the engine, it rejoins the airflow just after the engine afterburner, adding additional thrust as more oxygen becomes available for combustion and increases the pressure through the ejector nozzle. Air got into this bypass area in a number of ways. There was a shock trap, otherwise known as the cowl bleed, located here, which again helped minimize boundary layer growth. There were suck-in doors, located here, which only opened from Mach 0 to Mach 0.5, to add additional air to the bypass for engine cooling. Air from the aft bypass doors, located just before the J58 engine, also fed into the bypass. These, together with the forward bypass doors, which vented to the atmosphere, were used to control the pressure level in the inlet at the optimum level. If it was getting too high, a pressure sensor would trigger the forward bypass doors to open, allowing more air to exit the inlet, while the aft bypass doors were controlled by the pilot. These doors played a critical role in maintaining the position of the normal shock wave. If this was mismanaged, the engine would lose control of the normal shock wave and may even spit it out of the intake, resulting in a sudden power loss called an unstart, which would cause the plane to violently yaw in the direction of the faulty engine.
What
If this
the?
happened, the forward
Are you telling me pilots said this? Like, in today's world, feels weird, right? In today's anything, whether it's cars or anything you use, even like airplanes, helicopters, pilot basically has control of it, but doesn't have control of the run, like how it runs, basically engine or something. Like if a pilot fucks up, the engine fucks up. That doesn't happen in today's world. This is insane. Like at this level of technology, at this level of power and speed, a pilot fuck up can screw up the whole engine, right? They have control over this. Like, okay, this is insane. Like what type of pilot must be, must be with it, especially on the Soviet spaces. This plane used to fly over Soviet spaces, enemy space, like, like this is like a bleeding edge technology. US probably told you, like, don't you fuck up, they can't have this technology, don't you dare have the plane go down there, right? Basically crash there. And now you have this pressure of all that and you're flying this. What kind of like a training you must go through just to perfect this?
bypass doors would open fully, and the spike would move to the forward position to reduce back pressure and get the shockwave back into its normal position. Besides this bypass area that took air from the inlet and dumped it into the ejector, there were also 6 bypass ducts that took air from the compressor and dumped it directly into the afterburner. These ducts were the primary mechanism that transformed the engine from a turbojet into a ramjet. Afterburners are great. They significantly add to thrust without needing a whole lot of additional weight. They basically just inject fuel into the exhaust of the jet engine and ignite it with whatever oxygen is left to provide
Basically,
additional
turning into a
expansion
rocket.
and therefore thrust. But they are really inefficient. However, as the speed increases, they are the only feasible way to generate thrust, and they do gain efficiency thanks to the forward motion providing the compression of air needed to run them, instead of the turbine needing to be powered to turn the compressor stage. The crazy thing about the SR-71 is that the
Look at how it
engineers
looks,
could
man.
have eked out more thrust from this engine to increase the top speed even more. Ramjets can go up to Mach 5, so why did they stop at 3.2?
Because
Would
it
they have run out
disintegrated?
of fuel? Fuel efficiency in terms of cost doesn't mean a whole lot to a military plane like this. The military doesn't care about cost, but the more fuel you carry, the heavier and bigger the
Ergonomics,
plane
yeah.
gets, increasing the fuel it uses. There is a break-even point and the plane's range will be limited. But the engineers did manage to fill the plane up with an astounding amount of fuel with some clever engineering. The plane was strictly a surveillance plane, so no internal volume was used for weapons, freeing up space for fuel. You have probably heard that the SR-71 leaks fuel on the runway because there were gaps in the fuselage, but that's a simple fact that ignores much of the engineering that caused it. The SR-71 used something called a total wet wing fuel tank system, which meant that the fuel was not contained within a separate fuel bladder. This was a weight-saving measure. Separate metal fuel tanks would add too much weight, and lighter plastic ones would melt from the intense heat generated from the
Just put it
aerodynamic
in.
friction. So, the fuel was contained by the skin of the plane itself. The engineers applied
They just put it in. Oh god. Bleeding edge technology. What should we do? The best bleeding edge technology is like not have a tank at all. Just fucking pour it in. Seal everything up so it doesn't leak, and there you go. I love it. Whenever something like this comes, it's just fucking awesome. Obviously, it would have somewhat leak here and there. I'm guessing they come across very late. Like this is the best way to do is this rather than just completely early development, because they would have made some way to seal the plane in a way that doesn't leak. But by the end, like, okay, seal as much as you can, just fill up the plane. If some droplets leak, it leaks. This is so good, man. Only Americans would think that, like, okay, tanks is just like that doesn't work. Plastic doesn't work. Metal is just like, no, it's unnecessary. Just pour it in.
sealant to every gap the fuel could possibly come out of, But because the titanium skin of the plane expanded and contracted with every flight, it gradually deteriorated over time, allowing the fuel to leak out.
Makes
Because of
sense.
this, the SR-71 had to regularly go into maintenance and have sealant reapplied, but it usually came back still leaking, just not quite as much. The number of man-hours required to reduce it to zero was simply too great to fit it between flights, so they just had an allowable fuel leak.
Now I feel more active, energetic, and focused.
Between flights, so they just had an
The hell was on mute. So yeah, they should have just like add tank at this point, even if it means some inconvenience or something, right? Because if it this much of an issue like leak and everything and maintenance and sealant and all that crap, might as well have tank and whatever the issue that comes with it.
allowable fuel leak limit, which looked like this. This plane, like a rocket, was mostly fuel. Its dry weight, depending on sensor payload, was between 25 and 27 tons. Its wet weight was between 61 and 63 tons, making it, by weight, 59% fuel to feed those hungry engines. Even
30
then,
to 40
without the
tons of
ability
fuel?
to refuel in the air, this plane would have had terrible range for what was supposed to be a long-range spy plane. Range varied greatly. For example, the engines became significantly less efficient when the outside temperature was higher. A fully loaded SR-71
Makes
could
sense.
expect to burn nearly 13 metric tons of fuel, accelerating from Mach 1.25 at 30,000 feet to Mach 3 at 70,000 feet, if the outside temperature was 10 degrees Celsius above standard. That is 36% of its fuel capacity. If it
I mean, that makes sense, man. You realize the aerodynamics is everything in this plane, even with the works of the engine and everything. It relies on how air basically flows into and how it makes efficient that way. Yeah, it makes sense. Temperature would play that kind of a part.
was 10 degrees below standard, the fuel burn nearly halved to 7.2 tons. And of course, the range was severely affected by their speed and use of the afterburner. But on average, the SR-71 had a range of about 5,200 kilometers, about enough for a one-way trip from New York to London. Not terribly useful. The US was not going to be landing at their target to hand over a top-secret plane to the enemy. However, with aerial refueling, the plane could stay in the air more or less indefinitely, provided there was no mechanical issues. Really, the range was entirely determined by the pilots. The longest operational sortie occurred in 1987, when the US flew the SR-71 from Okinawa to observe developments in the Iran-Iraq War. This mission lasted 11.2 hours and likely required at least 5 aerial refuelings along the way. So,
Is there a guy who flew and stayed in a Blackbird for 11 hours straight? Just imagine that. Oh my god. I'm not gonna lie, it's a fun as fuck. From Okinawa all the way to Iran or whatever, flying through the sky, knowing you're untouchable. You don't need weapons because who's gonna do what? They can't even catch you.
if it wasn't the fuel or engines that limited the SR-71's top speed, what did? At Mach 3.2, the nose of the SR-71 reached 300 degrees Celsius, while the engine nacelles could reach 306 at the front and 649 at the back. This is what truly limited the top speed of the SR-71. Without careful material selection and design, the plane would simply overheat and fail. Even the fuel needed to be specially formulated to get around these overheating issues. It was a specially formulated fuel called JP7, which has very low volatility and a high flash point. This was partially needed because the fuel leaked on the runway, and they needed a fuel that wouldn't ignite or easily evaporate and make the ground crew ill. But mostly, they needed a fuel that wouldn't vaporize in the tanks and cause fuel feed and pressurization problems. The JP7 fuel was so stable that it actually doubled as a coolant for the entire plane. The fuel was pumped around the airframe to cool critical components like the engine oil, hydraulic systems, and control electronics. When the fuel got too hot, it was simply sent to the engines for combustion. The fuel was so stable that the plane actually needed to carry shots of triethylborane, a fuel.
Okay, they did all this, well, let's just say controlled technology, basically maintained by electronics in 1980s. I mean, I get it post Apollo, anything right after 70s and everything. US was at peak of that. They already went to moon and came back, so electronics were there. But still, in 80s, doing this kind of technology where they can basically put in the kind of measures like, okay, this fuel's gonna be act as a coolant, but when it gets hot, just throw it into the afterburner. All these like measures to put in there is just like insane.
That spontaneously ignites in the presence of oxygen to start the combustion cycle and afterburners. The plane usually only carried about 16 shots of this, so the pilots needed to manage them carefully, particularly when slowing down for refueling and managing unstarts. One huge question I had about the SR-71 was why it was painted black. Airliners are all white to reflect heat and prevent the plane from overheating. If that applies to an airliner,
so true.
why not the SR-71? The SR-71's predecessors were unpainted, which saved weight, and the areas exposed to highest temperatures were painted black. Why was this? Surely black would absorb more heat. The Concorde was once painted blue for a Pepsi ad campaign and had to lower its speed as it absorbed too much heat from the sun. However, the Concorde did not fly nearly as high or as fast as the SR-71, and as the SR-71 rose, the energy it absorbed from the sun dwindled in comparison to the heat it gained from aerodynamic friction. For this, we have to refer to something called Kirchhoff's rule of radiation, which tells us that a good heat absorber, like a black object, is also an equally effective heat emitter. So, the black paint helped the SR-71 radiate heat away from the plane, as it allowed the plane to radiate more heat than it gained from the radiation from the sun. These efforts helped to keep the plane cool, but the structure of
That is so true. It's a reverse, right? Black absorbs heat, so obviously it would like radiate it out as well if it like balances out that way. Same way, I guess fan works. The basic way of saying like if you're like feeling hot, you would start the room fan and you get cold. But if the room temperature is higher than your body temperature, starting fan would actually heat you up. Basically, it's some similar shit like that. Yeah, this is so awesome. Also, that's why certain things are painted black. When it's like, I'm pretty sure like, what is that plane? Spy type plane that has like a big ass wing, right? Even wings have their own will, and somebody constantly has to like make sure that it flies straight. Like it flies way too high, basically. That is also black, if I remember correctly.
the plane still needed to be incredibly heat stable. Aluminium is typically the material aircraft engineers turn to. It was used for the Concorde, but as we saw, it too had its speed limited by heat to a much lower Mach 2. Aluminium is cheap, has a great strength-to-weight ratio, and is easily machinable. Titanium, the material that made up 93% of the SR-71, has only one of these properties. Its strength-to-weight ratio, otherwise known as specific strength, is fantastic. But titanium is incredibly expensive, despite it being the 7th most common metal in Earth's crust. The refinement process is incredibly long and requires expensive consumables.
It refinements and the processing is much harder, even though there are way too many things that are like not rare, but the reason they're rare is because like the production thing is rare, right? Because it's really hard and the cost to material thing just doesn't work.
It's also not easily machinable, as it readily reacts with air when welding or forging, becoming brittle. For these reasons, titanium is rarely used in structural parts in aviation. However, the real benefit of titanium is its ability to resist heat. The reasons for this are complex that we will explore in depth in future. However, the gist is that titanium alloys have incredibly strong bonding within its crystal lattice that resist heat from breaking them apart. Titanium alloys can resist temperatures up to 600 degrees Celsius before their atoms begin to diffuse and slide over each other significantly, allowing it to retain much of its strength even at 300 degrees. It has also very low thermal expansion, so that expansion and contraction we mentioned earlier is minimized, reducing the thermal stresses in the aircraft. But titanium has its limits, and for the SR-71, this was about 3.2 Mach. Today, engineers have made huge strides in material science. The SR-71 used heat-resistant composite material.
Material science has gone insane in past few decades. So yes, if some replacement of SR-71 were to made today, how fast that would go? Like he said, like these engines can go up to 5,600 miles. I'm pretty sure like X15 is also, I don't know about X15. I need to find that video about that. But I'm pretty sure if the Blackbird was made today, it would easily do 5,000 miles per hour or something, because material science is like really insanely good today.
As radar-absorbing wedges between the structural frame, located in these locations. The manufacturing techniques needed to make composite materials as load-bearing structures did not yet exist, but that has changed. The SR-71 successor, the SR-72, which is now in development, will take advantage of new, high-performance composites, which will allow.
Why none of you said that in the comments? Everybody's like, having something like this is happening, this is somebody knows something all the time. None of you knew that SR-72 is in production? Or did I just miss a comment? There's a Blackbird replacement? Why? I thought there was satellite and drones replaced it. You need another Blackbird? Oh, this is gonna be awesome. When this is like, when Apollo mission was happening, everybody was just like living that time, was just excited, right? Like, we're gonna witness something awesome. This is basically similar to that. We're gonna have a new Blackbird. God knows how fast it's gonna be, or how overall it's gonna be. Yeah, that's gonna be insane.
Allow it to reach speeds up to Mach 6. Many of its engine components will likely be 3D printed titanium with cooling ducts printed right into the part. Its range also won't be determined by pilots, as it will be an autonomous drone.
Mach 6.
The insane engineering that makes planes like this possible fascinates me, and I recently watched an excellent documentary on CuriosityStream that details the build process for the world's largest airliner, the A380, chronicling the massive sheet metal cutting machines that cut the aluminium skin, the vacuum molds that form it, and the biggest oven in Britain that locks the shape in place. This is just one step in the process, and the documentary is nearly an hour long. This is just one of thousands of documentaries by award-winning filmmakers available on CuriosityStream right now, and
yeah, we'll go to original video page and from there support this channel. God, I love this SR-72. I hope somebody like Real Engineering or somebody just makes a video about it when the more information is known. Mach 6, god damn, it's like double. They're like, do you know Blackbird a few decades ago? We're gonna double that. Obviously that they could have doubled that then, but material science just wasn't there. Now it is. So yeah, I mean, this is just insane. Like Mach 6 plane. I mean, it just feels right? Like in modern world, there should be something like that. But yeah, I mean, F-15 did like Mach 2 plus, right? And newer planes, F-22 also did the same thing, 2.2 or something. I think F-15 did Mach 2.7 or something. I don't remember exact numbers. I don't remember. But yeah, modern planes are made more specific and surgical rather than fast. This is the first plane we're gonna have that's gonna be really fast, so it's gonna be fucking insane. Oh yeah. Alright, well, that was the insane engineering of SR-71 Blackbird. Watch out, Real Engineering. If you like my reaction, don't forget to subscribe. Comment down if you want to do any other reaction. If you haven't seen other reactions I've done recently about this type of thing, check out the link in the description, check out the end cards, and yeah, I'll see you next time.